everyone, welcome to our next video. Heading over to the notes. Today we're going to be going over 1.5. Just as a reminder, you will need to know all of this stuff from 1.4. So basically everything in this table, and then also being able to do, sine, cosine, tangent, cosecant at 30, 45, 60, 0, 90, 180, 270. You need to know how to do them in radians as well. And then we also want to be able to do like the in-between angles in the quadrants. So being able to do 30, 45, 60, and in every quadrant. So there's going to be like a 30, 45, 60 in each quadrant. It's just, the angle isn't actually 30, 45, or 60 anymore. It's going to be bigger than that. So make sure that you are practicing through those. We are going to use them as we do 1.5. So 1.5 is right triangle trig. And so first thing we have to go over is a little bit of inverse trig functions. Now I want to be specific here that when we do inverse trig functions, right now in this section, we are only going to find answers in quadrant 1. Later in 4.1, we'll talk about how to do them in all the quadrants, but just for right now, we're going to talk about only quadrant 1. The reason for this is I'm only going to talk about like 30, 45, 60, and then like, I guess technically the quadrantal angles maybe a little bit. So this is not like a full explanation of inverse trig. We just need just a little bit to be able to do some stuff in this section. So here's the gist of it. If you have an equation, say sine of an angle is equal to something, I don't know, let's call it, I'm just making up something here. Let's say it's equal to b. Now b is going to be an actual number and alpha would be an actual angle. If we want to use inverse trig says sine inverse of b would equal alpha. So sometimes the use for this is going to be sometimes we need to find alpha. So this is used for finding an angle. So if you know what sine of an angle is equal to, so you know b, you can do sine inverse of b to get the angle. Another common way to see sine inverse is you could see it written as arc sine. That is the same thing, sine inverse and arc sine. Now sine inverse is not the same thing as saying cosecant. Cosecant is the reciprocal of sine. It is not the same as sine inverse. So big distinction there. And I could do this with any of the trig functions. So if I say cosine alpha equals b, what if I know b but I don't know alpha? Well, I can do cosine inverse of b and that'll give me the angle alpha. And I could do it with tangent as well. I mean, I could do it with all of them. Now in 4.1, we'll go really in depth into this and, we'll have better like explanations and more of like a reason why and stuff like that. But just surface level right now. So let's do a little bit of practice. So example 1, we're going to find the angle for these. So I could also maybe just say like evaluate or something like that as the directions, either one. So for A, I'm going to ask you for sine inverse square root 3 over 2. Part B, I'm going to ask for cosine inverse of, let's do 1. C, we'll do a tangent inverse. Let's do 1 over root 3 for this one. Now I want to show you what I'm referencing back to. So I'm always going to kind of come back to that table and the coordinates that I showed you last time, like the coordinate plane. So I'm going to write it just off to the side real quick. So my table was, I have 30, 45, 60, sine, cosine. I'm just taking the main part of it. So this was 1 over 2, root 2 over 2, root 3 over 2. Cosine was root 3 over 2, root 2 over 2, 1 over 2. And then if I come to the coordinate plane, this point is 1, 0. This one up here is 0, 1, negative 1, 0, and 0, negative 1. This is 0 degrees, 90 degrees, 180 degrees, 270 degrees. And I could put the radians on here as well if we wanted to, but I don't think that we'll totally need it. So when I'm looking for sine inverse square root 3 over 2, I'm asking what angle would you plug into sine to get it to be square root 3 over 2. So I come to my table, I have sine, I look for square root 3 over 2. Okay, that happens at 60 degrees. So this equals 60 degrees. You can also write your answer in radians, I don't mind. So in radians, it would be pi over 3. Either will be correct for me. Next, let's do part B. So I'm looking at cosine inverse of 1. So I'm looking for an angle, remember that. So nowhere in my table does cosine equal 1. However, it does happen on this, on the coordinate plane. So it's probably one of the quadrantal angles. Remember that cosine corresponds with the x value. So I'm looking for, where does the x value equal 1? Well, that happens right here at 0 degrees. So this would equal 0 degrees, or in radians, just 0. A little bit harder of one, tangent inverse 1 over square root 3. Remember that tangent is sine over cosine. If we want to, we can always add tangent into my table. I'll bring it over to the side for a second. So if I need to, we can always add in tangent. Sine over cosine. So 1 over 2 over root 3 over 2 will be 1 over root 3. 45 will be 1. 60 will be root 3. So I'm looking for, where's tangent 1 over root 3? Well, that happens at 30 degrees. Or pi over 6 if you do radians. Now, you can also plug these into your calculator and you should be able to get the correct answer. So if we do part D, let's practice one where maybe it's like not a nice answer. So let's do sine inverse 0.8432. I have completely just made this up. So sometimes maybe you'll need to plug it into your calculator if it's not one of these nice values. So if you're not seeing 0, 1, or one of the ones in the table, you may need to just type it into your calculator. So let's see what I get for this. I'm just going to type it in. I get 57.48 degrees. Now be careful if they ask in my math lab, if they ask for degrees or radians, make sure you have your calculator in the right setting if you need to use the calculator. So this is it for the inverse trig kind of explanation. You just have to know that whenever you're dealing with inverse trig, you're looking for an angle. All right. Also, another thing I need to mention is when we use right triangles, and I kind of already talked about this a little bit, because we used right triangles in our last section. If alpha is here, this is your opposite side, this is your adjacent side, and this is your hypotenuse. Now, again, I already mentioned this whenever we did 1.4 because I knew that some people might already be familiar with that explanation. So should be some review for you. Also, I had mentioned before that sine of an angle is opposite over hypotenuse, and so on and so forth. I gave this in 1.4. So it's actually talked about in 1.5, but sometimes I go a little bit out of order from the book if it feels natural. So let's do an example. This says find values of all 6 trig functions. And this one gives us a triangle. So for this one, I'm going to put alpha up here. I'm going to do 1, 4, and that's it. That's all I'm going to give us. Obviously, this isn't drawn to scale. That's just something to know. A lot of times they're not drawn to scale. It would have been nice maybe if I drew it a little bit better, but I didn't. So, but don't get too caught up in that. So if I'm looking for sine of alpha, that's going to be opposite over hypotenuse. Well, I don't know the hypotenuse right now, but I can go get it. So let's call this, I don't know, C. Or we could call it R if you'd like, whatever you feel comfortable with. But we're going to use Pythagorean theorem to go get the hypotenuse. So last time I told you that R is equal to x squared plus y squared. This is just Pythagorean theorem. It just has the square root taken. So let's see, we'd get 1 squared plus 4 squared equals 1 plus 16, so square root 17. So now sine would be 1 over square root 17. Now something I just want to mention here is this is a good example of wanting to use the opposite adjacent hypotenuse explanation of sine, cosine, tangent, so on and so forth. instead of maybe the x over r, y over r explanation. The reason is because this angle is not in standard position. Standard position means it needs to touch the horizontal. This one is not touching the horizontal, so it's not in standard position. So we're not seeing sine be the y value over the r value like we usually would. So sometimes based on the orientation, we may want to use opposite adjacent hypotenuse instead of like x, y, and r and stuff. Also make a note here that in my math lab, they are going to want this rationalized, so that's the rationalized version. Let's do cosine. Cosine is adjacent over hypotenuse. So the side adjacent to my angle, that means touching it, is 4. So I get 4 over root 17. Rationalized, this is 4 root 17 over 17. Tangent is opposite over adjacent, so 1 over 4. You'll notice that tangent is also sine over cosine, so it would be 1 over 4, basically taking those numerators. Cosecant is the opposite of sine, or you can think of it as hypotenuse over opposite. So this is root 17 over 1, so just root 17. Secant is going to be root 17 over 4, and cotangent is 4 over 1, so just 4. Now this should feel really, really similar to the example we did last video in 1.4. I did one where like I gave you a point, but we still made a triangle. The only thing I did to change this one up is I made the angle not be in standard position. Let's do another one. This is example 2. It says solve the right triangle in which alpha is equal to 30 degrees and side C is 6. Now I want to make a little bit of a comment here. In general, a basic way to write triangles is to label them as A, B, and C, like the sides. Usually we're going to let A, B, and C. So A and B are your legs, and then C is going to be your hypotenuse, if we have one. Also, your angle across from A we would call alpha. Your angle across from B we would call beta. Your angle across from C usually we would call gamma, but in this case that's our right angle. It's our because C is our hypotenuse. Now it's totally fine if you switch where you put A and B. That is not going to be a problem at all. So let's go ahead and draw this triangle together. It's a right triangle. That looks terrible, but that's okay. Alpha is 30 degrees, and I can put alpha down here if we want, or we can put it up here. It is totally up to you. I like to put A at the bottom, so I'm going to make alpha up here. I'm going to say this is 30 degrees up here. I'm going to call my missing angle beta. Also, I know that side C is 6. Usually C is going to be your hypotenuse, so that's going to be 6. since this was alpha, I'll call this side A. Since this is beta, I'll call this one side B. Now again, I really can't stress enough that if you are drawing a triangle on your own, as long as you have alpha across from A, beta across from B, gamma across from C, your orientation doesn't matter. Like you can switch where you put A and B. So I'm looking for, when it says solve the right triangle, I'm looking for all my missing sides and angles. So of course I would like for you to pause and maybe try to do this on your own. And also try to think about what you would go for first. Like what would you try to get? I'll tell you that for me personally, I would try to go get angle beta. Because if I already know two angles, I know that triangles have to add up to 180. So I would do 180 minus 90 minus 30, which gives me 60. So I know beta is 60 degrees. And now I can try to find A and B. So I don't know. Let's pick A first. There is no reason that I'm doing that. I just am. I'm also going to label my beta. So with these, you often have options. Either I can try using, I definitely need an angle to help me, and I do have the hypotenuse. So if I think about 30 degrees, A, and 6, I can say that sine of 30 degrees would be equal to A over 6. Because remember, sine is opposite over the hypotenuse. So that's one way. And then I can solve this for A. Or I could use, maybe I want to use the 60 degree to help me. So I could say cosine of 60 degrees equals A over 6. Either way, I'm going to get the same answer. So I just want to point out to you that a lot of times you're going to have some options. So I'm going to multiply by 6 to solve this for A. So I have 6 times sine of 30 degrees. Now this is important. We know what 30 degrees is already for sine. So if I come back up to my table that I wrote up here, I have sine 30 degrees is 1/2. So I'm going to plug in 1/2. I get 3 is equal to A. Let me know if you're having any questions about this, of course. Send me an email. And I will point out to you, if you had done the cosine version, you'd have gotten the exact same answer. Now let's go find B. Again, with B, you're going to have some different options. Either we can use the trig functions again. So let's see if we want to do B. So it's the opposite side to 60. So if I want to use sine, I could do sine 60 is equal to B over 6. That's one option. If I want to do the 30 degrees, B would be the adjacent side. So I could do cosine of 30 is equal to B over 6. Or another way I could do this one is I can use Pythagorean theorem. So I know that A is 3. I know that the hypotenuse is 6. So I can use that to figure out what B is. So that would look like I can use good old Pythagorean theorem, A squared plus B squared equals C squared, and plug everything in. So that'd be 3 squared plus B squared equals 6 squared, and so on and so forth. So again, you definitely have options. I'm trying to get you a little bit more familiar with using the trig function, so I'm going to choose this first one that I wrote. So I'll multiply both sides by 6. Now sine of 60 degrees, we know what that is. I can go back up to my table to figure it out in case you don't know them by heart yet, which is fine. So sine of 60 is root 3 over 2. So I come back down here, root 3 over 2. So this becomes 6 times root 3 over 2. 6 over 2 can reduce to 3, and then I have the root 3 just hanging out. So B is 3 root 3. And if you had chosen any of the other ways, again, you would get the exact same answer. Of course, I don't need to see all of these different ways on the test or anything. I'm just showing you for the sake of the notes. That way you understand that there are different ways to get to the same answers. But whatever you like, whatever works for you, that's what you should do. Let's move into working on some applications. Usually when we say the word applications, we really mean word problems. So we're going to do some word problems. First, I want to review some geometry. So in geometry, we have this idea that if you have two parallel lines cut by a transversal, some of these angles are equivalent to each other. One of these examples of angles that are equivalent is these right here. So this is called alternate interior angles. So we're going to use this. This angle down here, we often call this the angle of elevation. What I want you to notice about the angle of elevation is that imagine like you're looking straight at something and then you look upwards at something above you. So let me give you an example. I'm going to guess most of you have been on campus at some point. So let's think about the clock tower. Let's say you're standing near the clock tower and you look up at the clock. That movement from you like looking straight as you're walking to then looking upwards, that makes an angle of elevation. Then we have something called the angle of depression. So let me draw this one for us. It's here. This is the angle of depression. So this one, imagine you're looking straight and then you look downwards at something. So let's say you are walking and then you see something on the ground. You're going to look slightly downwards at that thing on the ground. So when you're going from like eye level to then looking downwards, that movement there is an angle of depression. Something really important to know about the angle of depression is it always, and the angle of elevation, they always need to be touching the horizontal. So for instance, sometimes I'll have people, it's a word problem and it's describing a right triangle and they say angle of depression. Sometimes students will put it up here. This is incorrect because it's not touching the horizontal. The angle of depression would be here. And then something else to remember is that the angle of depression and the angle of elevation are equivalent to each other because of alternate interior angles. So the angle of depression and the angle of elevation are equivalent angles, and they always need to be touching the horizontal when you draw them out. So I'll maybe make a point to say that. Always touch horizontal. I ran out of space. So let's go ahead and do some word problems and we'll practice and we'll see all of this come together. So example 1, this would technically be example 3. Example 1 under applications, but really it's example 3. So this says that from the steps of Wiley, sorry, my pen wasn't writing. It's because sometimes my wrist touches a certain part of the iPad. Oh, this is funny. Hold on, someone told me this recently. Wiley doesn't have an E in it. Is that true? I'm about to look it up to make sure. I want to make sure that I write this correctly, but this is kind of a funny little piece of information for you guys. So last quarter actually, my students pointed out that I had wrote Wiley, and they were like, all the math people spell it that way, but there is no E in Wiley, like for Wiley Tower here at Tech. And I thought that was so funny. And the reason is because, oh goodness, I'm spelling it wrong 2 different ways. This is funny. I'm not going to edit this out. Y'all can just enjoy the funny misspellings that I make. So I wrote it like this just now. That is a textbook company. That is not like Wiley Tower here at Tech. Wiley Tower is spelled W-Y-L-Y. Yeah, I had just last quarter someone brought that up and I was a little embarrassed, but I do think it is pretty funny that I was doing it for kind of a while, like spelling it wrong. So anyway, let me finish writing the problem. Hopefully you think that's funny, but from the steps of Wiley Tower, the angle of elevation to the top of the clock tower is 30 degrees. if the distance from the steps of Wiley to the base of the clock tower is 1,200 feet, what is the height of the clock tower? So of course I recommend pausing, that way you can go ahead and write this down, but I am just going to go ahead and get started. First, I always like to draw a little bit of a picture, as best as you can. Sorry if I just hit the mic. So Wiley Tower, we'll draw it here, and I got these steps. And so we're really saying from the steps, so from these steps, and then we're like looking upwards at the clock tower. So let me draw the clock tower. I'll put this little thing at the top, that way you know it's the clock tower. So this is Wiley, this is the clock tower. And we know that the distance from the steps to the base of the clock tower is 1,200 feet. So I'm going to write that in, 1,200. I'm using this as a right triangle. I know that because the ground is drawn horizontal and then to the vertical clock tower, so that would be a right angle. Now usually on the test, I like to say something like, assume this is a right triangle. Because I guess naturally, ground was have curvature and stuff like that to it. But we don't really have to worry about that right now. And so let's see. The angle of elevation to the top of the clock tower from the steps. So we got to think we're looking from the steps. So imagine we're looking straight and then we go to look upwards at the clock tower. That is an angle of elevation. So right here will be my 30 degrees. And this should really be drawn to the top, but it's not perfect, so that's okay. And we're looking for the height of the clock tower, so let's see, I'll just call this H. Now the picture would be something that, you would draw on like a test or something. So you would have to draw the picture yourself. Usually I say, please draw a picture. Okay, so now we need to think about what sides of our triangle we have right now. So I'm looking for the opposite side, like across from the angle would be the opposite side. I'm given the adjacent side. I don't know anything about the hypotenuse. So now I want to think, do we know a trig function that includes the opposite side and the adjacent side only? And so answer that, I guess, to yourself. But it would be tangent. So if I do tangent of 30 degrees, remember tangent is opposite over adjacent, so it'll be h over 1,200. Now I want to solve this for h. So if I multiply both sides by 1,200, I get 1,200 times tangent of 30. Now we know tangent of 30 If you don't know it by heart, maybe you know the table and we can go get it. So I'm going to scroll up real quick just to go back to my table. So let's see, right now, I don't want those circled. I'm looking at tangent 30 degrees. So that's going to be 1 over root 3. So I come down here. So tangent of 30 is 1 over square root 3. Now I'm fine with you writing your answer like this and just boxing that in and being finished. However, please be aware that my math lab is going to want you to rationalize. To rationalize this, I would take 1200 over root 3 and I would multiply by root 3 over root 3, which equals 1200 root 3 over 3. 1200 divided by 3 would be 400, and then I'm left with the root 3. So I'll take either one of these answers, rationalized or not. I'm okay with either one. But my math lab is going to want you to rationalize. Now I want to make a comment here. If I had said the angle of depression from the clock tower from the top of the clock tower to the steps of Wiley, I almost spelled it wrong again. Steps of Wiley is 30 degrees. Let's say that for this question, instead of giving you the angle of elevation, I gave you the angle of depression. It would not change anything about what we just did. Absolutely nothing. Because the angle of depression is not right here. If you put it right there, yes, you'll get the answer incorrect. It should go up here because it needs to touch the horizontal line. And then maybe we would have preferred to draw our triangle this way. And we would have said this is 1200 and this is the height. Or maybe you do realize that these two are the same and you just draw it down here instead. There's definitely some options of how to kind of work with your answer, but I really just want to make the point to you that I could give you angle of elevation or angle of depression. And for this problem in yellow is what it would look like if I had given you angle of depression instead of angle of elevation. Like that's how the wording would have said, because it would have been like from the top of the clock tower, so you're looking straight, to the steps of Wiley, so you start looking down. So it's that movement from looking straight at something and then looking downwards. That's the angle of depression. All right, I'm going to go ahead and do another example. So this is example 4. This one says the angle of depression from an airplane in the sky to a runway is 45 degrees. So what we're looking at here is we've got an airplane flying in the sky and it's like going to start to land. So it's kind of landing onto the runway. So how far is how far diagonally, I missed a word, diagonally is the plane from the runway when the plane is at an altitude of 7,000 feet. So let me read this for us again. The angle of depression from an airplane in the sky to a runway is 45 degrees. How far diagonally is the plane from the runway when the plane is at an altitude of 7,000? So let me go ahead and draw what we have going on. I'm not going to draw a plane because that would probably just be pitiful. I'm just going to write the word plane. So we got a plane flying in the sky, and he's landing onto the runway. And it says the angle of depression from the airplane to the runway. So this one I think is actually a little easier to notice where it should go. So you imagine, the plane is flying straight, and then it's going to have to start going downwards to land. So that's the 45 degrees. That's the angle of depression. Then we're also given the height of the plane. So I'm going to draw that over here. So it tells me that the plane is 7,000 feet altitude, so in the air. And I can make this a right triangle. And again, I usually say for these, assume this is a right triangle. Now we're looking for this diagonal distance. So we're looking for this distance here. I'll just call it D for distance. You can call it whatever you want. And so again, let's think about what we have according to our angle. So my angle is across from 7,000, so that's my opposite side. And then the D is my hypotenuse. So I need a trig function that connects the opposite side and the hypotenuse. And the one that does that is sine. So I'll have sine 45 degrees is equal to 7,000 divided by D. Now let's go ahead and solve this for D. So if I multiply both sides by D, I get D times. Now I know what sine of 45 degrees is, so I'm going to go ahead and find it now. You don't have to do it now if you don't want to. You can do it later. Sine of 45 degrees, if you go up to your table, which I will, we're looking at sine 45, it's root 2 over 2. And of course, you want to be able to get pretty good at recognizing those. So root 2 over 2. And now I need to solve this for D. So you can think of it a few ways. You can divide by root 2 over 2. You can multiply by 2 over root 2. There's definitely some options. This part's just algebra. So let's see. I'll multiply by 2. That gives me D times root 2 is equal to 14,000. And then I'll divide by root 2. You can do this in a few less steps, but this is just how I'm doing it today. Now, just as a reminder, My math lab is going to want this rationalized, so I would do times root 2 over 2, times root 2 over root 2, which will give me 14,000 root 2 over 2, which simplifies to 7,000 root 2. I'm okay with either of these answers, but the homework is going to want the rationalized version. Again, rationalized means no radical in the denominator. So if you have any questions about this, please do let me know. There's different ways to solve that one, so just be careful. I've had people do this in the past, like they solve it for D in the beginning, so they get D equals 7,000 divided by sine of 45. Now sine of 45 is root 2 over 2. But remember, when you divide, that's the same as multiplying by the reciprocal. So this is the same as 7,000 times 2 over root 2. Because when you change it from division to multiplication, you have to flip the fraction. You may have learned it as keep, change, flip, or something like that. All right, so I'm going to keep on going on over to our next example now. Just be careful with the algebra of that one. Let's see, is that example? Yeah, there'll be a 5. This one is a little longer of a problem. It is a little bit harder. So it says the angle of elevation of the top of a water tower from point A on the ground is 19.9 degrees. From point B, 50 feet closer to the tower, the angle of elevation is 21.8 degrees. And we want to know what is the height of the water tower. Now, something to know is we are going to need a calculator for this one. The reason is because we have bad angles. So oftentimes on the test, especially test 1 and test 2, I like to give you, 30, 45, 60, or other angles that have what we call a reference of 30, 45, or 60, like in 1.4, where we can always reference back those angles. If you see a problem on the homework that has kind of weird angles and stuff, just know that on the test, I will be giving you nicer angles, okay? I'm not going to give you angles that you have to use a calculator for because I do recommend students who are engineering and science majors to maybe try to do the test with no calculator, at least test 1 and test 2. Test 3, you absolutely need a calculator, but 1 and 2, you can take them without one. But this question, we are going to need them. So of course, I'm going to go ahead and draw our situation. So we have, let me draw our water tower first, as best as I can. They always have these little lines on the bottom of it, I feel like. Oh, I just hit the mic, sorry. So it says the angle of elevation of the top of the tower from a point A on the ground. So we're at point A on the ground and we're like looking up at the top of the tower. We can say that we're ground level with the tower. So that is 19.9 degrees. Then it says that there's a point B 50 feet closer to the tower. So 50 feet closer, that would make this 50 feet. We have B, and the angle of elevation from this point is 21.8. Now it should make sense that if you get closer to something, your angle is going to get bigger, right? Because if you get closer, you're going to have to look up more. So your angle of elevation is going to get bigger. Now let's see, I'm looking for the height. So I'll call this H. I'm looking for the height of this tower. I would like some more information. I know a little bit about the horizontal information, but not that much. I don't know how far this is. Let's go ahead and call it X. That would also make this whole distance right here X plus 50. So the reason I'm trying to work with that horizontal distance is because at least they told me something about the horizontal distance. They didn't tell me anything at all about the diagonal distance. And I'm looking for the height. So now we want to think about what we have going on. So I have all this information about horizontal and the vertical. So the opposite and the adjacent. So I want to think of what trig function includes the opposite and the adjacent. And that is going to be tangent. I also have two triangles going on. I have this smaller triangle inside of here, right? And then I also have this bigger triangle out here. So I have two triangles happening here. I'm going to write an equation for my smaller triangle. My smaller triangle, I'm going to scroll down a little, is tangent 21.8 degrees is equal to height over x. Now my bigger triangle also has tangent. 19.9 is my angle in there. And it's h over this whole side here, which is x plus 50. So now I have two equations and two unknowns. That's really why we needed two equations, because we have two unknowns. And anytime you have two unknowns, you need two equations. You have three unknowns, you're going to need three equations, and so on and so forth. So I'm looking for height. So what I really want to do is find out a way to compare these two equations maybe set them equal to each other if we can, or something like that. So let's see. Since both of them involve h, let's go ahead and solve them both for h. So if I solve the pink one for h, I would get x times tangent 21.8 degrees is equal to h. And for the green, I would get x plus 50 times tangent 19.9 degrees is equal to h. Now I want to make a little bit of a point here. So with this situation, ideally we have options, okay? We can either have it equal to h and set them equal to each other, solve for x. The problem with that is that then we have to, once we get x, we'll have to plug it back in to get h because we don't want to lose what we're looking for. We're looking for h. So if we set them equal to each other right now, we're going to lose the h and we'll have to solve for x. The other option is to solve both of these for x right now, set those equal to each other, and solve it for h like that. The issue is I worked both ways out, and honestly, I think that solving it for h like we have it, setting it equal, and then solving for x and plugging it back in, I actually think is a little bit easier algebraically. If you solve both of these for x right now and set them equal to each other and solve for h, it's just harder algebraically. But I just want to point out that technically there's two different ways to approach this problem, and you could choose either one. So what I'm going to do, because I do find it a little easier algebraically, is I'm going to leave them both set equal for h. Since they are both set equal to h, I can set them equal to each other. So I'm going to set this equal to this, basically ignoring the h's since they're both equal to h, so they're equal to each other. So this would be x tangent 21.8 degrees is equal to x plus 50 times tangent 19.9 degrees. So again, the other way to do this problem would be to set them equal to x first and then set them equal to each other, and you'd have h in there, but it is harder algebraically to work with. I really hope that makes sense. If not, don't stress about it too much. So I'm going to solve this for x. So I get x tangent 21.8 degrees. To solve this side, I really need this x out of the parentheses. So to do that, I'm going to distribute. So I get x tangent 19.9 degrees plus 50 tangent 19.9 degrees. Now, just like with a normal equation, we want to get our variable that we're looking for on one side. So I'm going to get my x's on the same side to do that. Let me show a little bit of work here. I'm going to subtract this from both sides. That way I have the x's both on the left. So I'll have x tangent 21.8 degrees minus x times tangent 19.9 degrees is equal to 50 tangent 19.9 degrees. Now I want to get this x by itself. Usually we would try to combine like terms at this point, but these cannot combine. What I can do is I can take an x out from both of them and factor it out to the front. So my step right here of what I'm about to do is I'm going to factor out the x. So if I take the x out to the front, that leaves me with tangent 21.8 degrees minus tangent 19.9 degrees, all in parentheses, equals 50 tangent 19.9 degrees. Now I can divide by tangent 21.8 degrees minus tangent 19.9 degrees. So I'm going to divide out this whole thing right here and divide it on the other side. I don't want to write it twice, so I'm just going to write it once. X equals be 50 tangent 19.9 degrees over tangent 21.8 degrees minus tangent 19.9 degrees. Unfortunately, we are not finished because that's only the x value. That is not h, and we need to find h. But I can go get h. So let's look over at this equation here. To find h, I'm supposed to take my x value and multiply by tangent 21.8. So I can do that here. You could also use this equation, but the one on the left looks easier to plug into. So that's why I picked that one. Technically, you could use either one. Maybe a good way to check yourself would be to plug them both in and see if they're the same. They should be. So I get h is equal to, I'm going to plug in my x, which is 50 tangent 19.9 degrees divided by tangent 21.8 degrees minus tangent 19.9 degrees. And I'm going to multiply this by tangent 21.8 degrees. I'm running out of space. Let me write that better. 21.8 degrees. Now again, just as a reminder of what I just did, I looked at this equation up here, trying to get your attention. So up here, the one I circled in yellow, and so I plugged in the x value, which is what I just solved for, into that equation. Now you got to type it in the calculator. Now when you type this in the calculator, please make sure you keep a parentheses around just the denominator. You can type it all in at once, but definitely be careful, okay? What you should get for your answer is that h is equal to, I'm actually going to plug it into my calculator. I have the answer in my notes, but sometimes I don't trust myself because I don't know how long it's been since I wrote it. So I don't know. It's not like it changes over time or anything, but I still get worried that maybe I did something wrong and I just never fixed it or something like that, you know? So the answer that I got is 190.63. So this is our height of our clock tower, and this is in feet, by the way. So that was a pretty wild one. Okay, let me give you some good news. If you tuned out in the middle of any of that, you have good news. This is not on the exam. I don't test on this question. I like it. I like this question. I think it's great algebra review. Um, but I usually find that students are struggling a little bit in the algebra department. So doing this, I don't want to mess you up too bad. I do like the ideas in this one though. Now, for those of you who are going to go into Math 240, this is exactly the type of question you'll be expected to do in there. Like doing something like this would be completely valid in that class. Kind of having these two different equations and setting them up and stuff like that. There's a whole modeling section that y'all will do, and you guys will do stuff similar-ish to this. But yeah, so good news. I don't test on this question. The ones you'll see on the test are a bit more similar to example 3 and example 4. I like to use those. But you do have a homework question like this one, so I still like to do it and stuff. So that is it for 1.5. I hope everything is going well in the course so far, and I will see y'all in the next video. Bye-bye. Have a good day.